So what if the secret to making AI more reliable wasn't about building a smarter AI, but about building a smarter team of them? Today we're diving into this really cool idea, creating an entire AI office to catch mistakes before they ever become a problem.
All right, let me ask you something. Would you bet your entire company on just one employee? No oversight, no one double-checking their work? Just one person handling your most critical tasks? I mean, of course not, right? That would be crazy.
You see, a single worker, no matter how brilliant they are, is always going to be a single point of failure. But a team, an office, well, that has structure, peer review, checks and balances, and that leads to way more reliable work. And it turns out that exact same logic might just be the key to building AI we can actually trust.
So here's what we're going to cover. We're breaking down a research paper that makes this very case. We'll look at why a single AI is a big risk. Then we'll see how to build this AI office. We'll meet the team of rivals that works there and understand the clever defense system they use. And of course, we'll look at the real-world results and talk about the true cost of all this trust.
Okay, so first things first. What is the fundamental problem we're even trying to solve here? Well, it all boils down to the unreliability of a single AI agent. This idea of the lone genius.
The paper puts it perfectly. When a single large language model, the engine behind tools like ChatGPT, when it hallucinates or just gets something wrong, there's no safety net. That mistake just keeps going. And in really important fields like finance or healthcare, a single uncaught error, well, that could be catastrophic.
And yeah, that's pretty much how most AI systems work today. We hire this brilliant digital analyst, give it a task, and just trust the output. For low-stakes stuff, hey, maybe that's fine. But for anything mission-critical, it's like walking a tightrope with no net. It's a massive and often invisible risk. So let's get to the solution, because it's a really powerful one. The paper suggests this radical shift in thinking. Stop trying to hire a solo AI genius. Instead, start building an entire AI office, one with structure, different roles, and most importantly, oversight.
The whole goal here is to achieve something the researchers call coherence. Now, this isn't about compromise or majority rule. It's about engineering a system where different AI agents, which are designed to have conflicting priorities, all have to agree that the final result is acceptable. It's a unanimous decision, or it's a no-go.
So who exactly works in this AI office? Let's meet the key players, because this is where it gets really interesting. This is the team of rivals.
First up, you've got the planners. Think of them as the strategists, the architects. They take what you want, map out a super detailed step-by-step plan, and, this part's absolutely crucial, they define exactly what a successful outcome looks like before a single line of code is written. They literally set the rules of the game.
Then you have the executors. These are the doers, the project managers. They take the blueprint from the planners and they make it happen. They route tasks to specialized agents who actually do the work, like writing the code. Their job is simple. Follow the plan, get it done.
And finally, we have the most important rivals in the whole office, the critics. These guys are the gatekeepers, the quality control. They are totally independent, and their only job is to evaluate the finished work against those success criteria the planner has set up at the very beginning. And they have absolute veto power. If the work isn't good enough, it gets sent straight back. No questions asked, no exceptions.
So, how does this whole team structure actually stop mistakes from slipping through the cracks? Well, the entire system is based on a classic model from safety engineering.
It's called the Swiss cheese model, and it's a brilliant analogy. Picture each AI agent as a slice of Swiss cheese. It's pretty good, but it's not perfect. It's got some holes in it. Now, an error can easily get through one slice. But what happens when you stack multiple slices of cheese? The holes don't line up, and suddenly you have a solid barrier that errors can't get through. That's the core idea here.
In practice, this plays out in what's called the critique loop. It's simple, but it's so effective. An executor agent writes some code. A critic agent immediately evaluates it. If it's rejected, boom, it gets sent back for a retry. If it's approved, and only if it's approved, does the work get to move on to the next stage. It's a constant loop of writing, checking, and revising until it's perfect.
Okay, so this all sounds fantastic in theory, right? But the real question is, does it actually work? Like in the real world, in a production environment? Let's take a look at the data.
This chart is awesome. It shows you the whole system in action across 522 tasks. Just follow the flow from left to right. You see that big blue river on the left? That's all the initial work. The purple streams are all the times the critics sent work back for revisions. And notice how that flow gets refined and filtered at each step. By the end, look how tiny that final red rejected stream is compared to the big green approved one. Almost every single error is caught and fixed internally.
And what's the end result of all that filtering? A final success rate of 92.1%. That is incredible. That means for more than 9 out of every 10 tasks, the AI office produced a perfect result with 0 human cleanup needed. So, how did it get there?
Well, the real hero is that first line of defense. The internal critics catch and fix almost 88% of all the initial errors. Just pause and think about that for a second. These are all mistakes that a normal, single AI system would have just passed right along to you.
So after all of those internal checks and balances, the final error rate that ever makes it to a human user is just under 8%. And the paper found that even most of those weren't really failures, but times the AI needed a human to clarify an ambiguous request. The big takeaway here is that the AI office deals with nearly all of the potential problems before you even know they exist.
Now, as you can probably guess, achieving this kind of trust, this level of reliability, it's not free. There's a very clear trade-off you have to make.
This table really breaks down what you're paying for. A single-agent system, it's basically a black box. Your data is exposed, its reasoning is opaque, and it's reviewing its own homework. The AI office, on the other hand, gives you multi-layer validation, a complete audit trail of every decision, and it keeps your data safe. It's really the difference between a wild guess and a verifiable, auditable answer.
And here is the price tag for all of that trust. It costs about 39% more in terms of computation, and it takes about 22% longer. So no, it's not the fastest or the cheapest way to do things. But if you're dealing with critical infrastructure, financial data, or patient records, paying a little more to prevent a catastrophe starts to sound like a pretty fantastic bargain.
And that leaves us with one last big idea to think about. As these AI models get more and more capable, maybe the race isn't just about making them smarter anymore. Maybe the real frontier, the next great challenge that will unlock their true potential in our world, is all about making them provably, structurally trustworthy.
Okay, let's dive right into something pretty cool. We're looking at a brand new framework called ThinkSafe, and it's trying to solve one of the biggest, most complicated puzzles in AI development right now.
And that puzzle, well, it's this question right here. As we keep pushing AI models to get better and better at complex stuff like math and coding, what if we're accidentally, making them more dangerous? It's a really critical issue, and it's exactly what we're going to unpack.
So to really get what the solution is, we first have to wrap our heads around the problem. And researchers have a name for it, the AI safety tax.
What in the world is a safety tax? Well, think of it like this. It's this super frustrating trade-off. When you train an AI to get really good at one thing, like, say, super complex logical thinking, it can actually get worse at another thing, like remembering its own safety rules. You're basically paying for that improved reasoning power with a tax on its safety.
But why does this even happen? Well, during this intense training, the AI is basically just trying to get the highest score possible, to maximize the reward for getting the right answer. And in that process, the original safety training it had, it can just get buried or even totally ignored. The model learns that the reward is the only thing that matters, and sometimes that's at any cost.
So this brings us to what's called the alignment dilemma. Researchers have been trying to fix this safety tax for a while now, but, well, the old ways of doing it had some pretty serious flaws. The two main approaches have been, first, teacher distillation. That's where a smaller student AI learns safety from a bigger, more powerful teacher model. And the second is naive self-distillation, where the AI basically tries to teach itself how to be safe. Both of these sound pretty logical, right? But it turns out each one has a fatal flaw. The problem with that teacher-student method is this thing called distributional discrepancy. It's a fancy term, but the idea is actually super simple. Imagine you're trying to learn how to write by perfectly tracing someone else's handwriting. Sure, you'll copy the letters, but you'll never develop your own natural style. That's what happens here. The student AI is forced to mimic a style of thinking that isn't its own, and that mismatch actually makes it worse at what it was already good at.
Okay, so what about the model teaching itself? Well, here's the kicker. Because it's been so heavily trained to be helpful and follow instructions, it acts like an extreme people pleaser. When you give it a harmful prompt, its first instinct is to try and answer it, not to refuse. It literally struggles to say no safely because its own programming to be helpful gets in the way.
So, if the old methods are broken, what's the new idea? This is where we get to the really brilliant part of the ThinkSafe framework, this idea of unlocking what they call latent safety.
And this is the aha moment. The researchers figured, what if the model hasn't actually forgotten how to be safe? What if that knowledge is still in there, just dormant, suppressed by all that other training? The real challenge isn't to teach it something new, it's to help it remember and access what it already knows.
So how do they pull this off? It's this super elegant four-step process. First, they give the model a harmful prompt. But then, and this is the absolute key, they add a special little note, an instruction that basically says, hey, this prompt is harmful. You should refuse to answer it. That little nudge is all it takes to guide the model to find that hidden safety knowledge and generate its own safe, smart refusal. And then for the final step, they fine-tune the model on its own high-quality answer. It's literally learning from the best version of itself. And the result of this? You get a response that is not only safe, but it's also perfectly true to the model's own unique way of thinking. It's completely in distribution, as they say. Because the model is creating its own training data, it totally avoids that distributional discrepancy problem we talked about earlier. It gets safer without messing up its own native style. Okay, the theory is fantastic. It's elegant, it makes sense. But, the proof is in the pudding. Did it actually work? Let's look at the data.
The results are, well, they're not just good, they're kind of jaw-dropping. Just look at this one model, Qwen34B. Before they applied ThinkSafe, its harmfulness rate was over 38%. After, that number plummeted to under 10%. That's a massive, massive improvement in safety.
But this brings us right back to that million-dollar question. Did they just pay the safety tax? To make it safer, did they have to make it dumber?
No. And this is the part that is a total game changer. Its reasoning score didn't just stay the same or go down a little, it actually went up by more than 2.5%. ThinkSafe didn't just avoid the safety tax, it completely flipped it on its head. The model got both safer and smarter.
So how does this stack up against some of the other, more complicated methods? Well, let's compare it to a big, computationally expensive method using reinforcement learning. That method takes over 21 hours to train, and it still ends up with a 37% harmfulness rate. ThinkSafe? It gets a better safety score, and it does it in just 2.6 hours. It's not just more effective, it's almost 8 times faster. Incredible! Okay, let's zoom out for a second. What does a breakthrough like this actually mean for the big picture of AI? So, to tie this all together, we've seen that this safety tax is a very real problem. We know the old ways of fixing it didn't really work because they created this weird mismatch in the AI's thinking style. The absolute genius of ThinkSafe is that it just guides the model to unlock its own hidden safety knowledge. And by teaching itself, it keeps its unique abilities, which gives us a much faster, much more efficient way to create AI that is, finally, both safer and smarter. And that leaves us with this one final, fascinating question to chew on. This research proves we can help a model access parts of its own knowledge that have been suppressed. So if we can teach an AI how to consciously refuse, what other hidden abilities are just waiting in there to be unlocked? What else can we teach an AI about itself? All right, let's get right into it. We've all been there, right? You're talking to an AI, and it's incredible. It can write a poem, break down complex science, you name it. But then you ask it to remember something you told it 5 minutes ago, and you get nothing. It's like talking to a genius with a case of amnesia. And that's exactly what we're going to unpack today and look at a really cool fix for it. It's a fantastic question, and it feels completely backwards, doesn't it? I mean, how can something so powerful struggle with something so basic, something any of us could do without a second thought? Well, it turns out this isn't some random glitch. It's actually a core challenge baked into the very design of how these AI models work. So the main culprit here has a name: the context window. The best way to think about it is like the AI's short-term memory, or maybe its desk space. It can only hold so much information at once. As you keep talking, the desk gets cluttered. And to make room for new stuff, the AI literally has to shove the oldest things off the edge. So that name you mentioned at the start of the chat? Yeah, it just fell off the desk. Now, researchers have been wrestling with this memory problem for a while, and the go-to solutions have always centered on one thing: text. Just more and more text. But, as we're about to find out, trying to fix this with just a long, boring line of words creates some pretty big problems of its own.
This really shows you what I mean. The old methods fall into two camps. First, you have what you could call the raw history approach. The AI just grabs a messy chunk of your past conversation. The problem? It's full of junk, filler words and tangents that eat up that precious memory budget. The other method is the text summary. The AI tries to be smarter and writes a little summary of the chat. It's a step up for sure, but it's got this one huge hidden flaw.
And here is that flaw. It's called uniform information density. It's a fancy term for a simple, kinda dumb problem. In a text file, every single word costs the exact same amount of memory. So, a useless word like the takes up the same space as the critical piece of information you're looking for. The AI has no way to signal, hey, this part right here is super important, but all this other stuff is just fluff. It's incredibly inefficient.
Okay, so this is where things get really interesting. What if we stopped trying to force AIs to remember things in a straight line of text? What if, instead, we let them remember things the way we do, visually? This is a huge change in thinking, a total paradigm shift for how we approach AI memory.
And the researchers behind this new technique, called MemOCR, they put it perfectly. They call it a paradigm shift from 1D textual memory to 2D visual memory. We're literally going from one dimension, a line of text, to two dimensions, a rich visual canvas where information can be organized in a much smarter way.
So here's the best way to think about this. One-dimensional text memory is like reading a book. You just go word by word, from start to finish. But two-dimensional visual memory, that's like looking at a mind map. And what's the first thing you do on a mind map with the main idea? You write it in the middle, you make the font huge, you put a circle around it, you give it visual importance. And that is exactly what this new method lets an AI do.
And this superpower has a name too. It's called adaptive information density. It's the perfect solution to that old problem. Now the AI can be strategic with its memory. It can make the crucial facts big and bold so they're easy to see, while it shrinks the less important details into the background. It's all about packing way more useful information into the exact same amount of space. Okay, so an AI creating a visual mind map of its memory sounds really cool, but how does that actually work? How do you get a large language model to suddenly think in pictures? Well, let's break down the mechanics of MemArcata. It's a really clever two-step process.
First up is memory drafting. The AI doesn't just write a boring summary anymore. It acts like a designer, using a format like Markdown to add headings, bold text, and bullet points to flag what's most important. Then comes step 2, memory reading. That structured text is turned into an actual image. That image is the AI's new memory, and when you ask it a question, it literally looks at the image, scanning for the big headlines first, just like you or I would scan a web page.
You can see the whole elegant cycle here. It starts in the text world, where the AI agent is drafting and updating its rich text memory. Then that text goes through a renderer and becomes an image, a visual memory. Now it's in the vision world. From there, the AI can just read the image to find the answer it needs. It's this amazing pipeline, moving from text to vision and back to a final answer.
So this is a very cool, very clever idea. But the big question is always the same. Does it actually work any better? Does turning memory into a picture really help an AI when the pressure is on? Let's take a look at the results.
And wow, the data is pretty dramatic. This chart shows what happens when you really squeeze the AI's memory budget. The old text-based method just falls off a cliff. Its performance plummets by almost 50%. But MemMCR, the visual method, it degrades so gracefully. Its performance only dips by about 10%. It handles the pressure so much better.
So what does that actually mean in the real world? It means MemOCR can get the same job done with the same accuracy using 8 times less memory. Let me just say that again, 8 times more efficient. That is an absolutely massive leap in how we can use that limited context window.
But honestly, nothing shows the difference like a direct visual showdown. For this test, the researchers set up a really tough challenge. They asked the AI a specific question and gave it a ridiculously tiny memory budget to work with, just 16 tokens. I mean, for a text-based AI, that is barely enough for a short sentence. It's brutal.
And the results are just night and day. On the left, you see the standard text memory totally failing. With such a tight budget, the answer just gets cut off. It's lost. In the middle, another visual approach without smart layout also fails because the text just becomes an unreadable smudge. But on the right, MemOCR succeeds.
it manages to hold on to that one crucial piece of information. And this is exactly why it works. Look at that. In its visual memory, the AI made the songwriter's name a big, bold headline. So even when the image got compressed and all the other details blurred into nothing, that critical fact, it stayed perfectly readable. It saved the evidence. That is the power of this adaptive visual approach. So this is way more than just a cool academic trick. Giving an AI a memory that's this much more efficient and reliable, it has huge implications for what we can actually do with this technology. This really changes the game for any kind of complex, long-running task.
So what does a future with this tech look like? Well, for one, you get AI assistants that actually remember your conversation from yesterday or even last week. You get AI agents that can tackle massive research projects, holding all the key facts in their mind at once. It means better personalization, more reliable systems, and just all-around more capable AI partners for all of us.
And that really brings us to the big final question to think about. Forgetting that limited context window has always been one of the biggest things holding AI back. If we can really start to solve that problem, what becomes possible? What could you create or solve or discover with an AI that has a truly reliable long-term memory? It's a pretty exciting future to imagine.
You know, when two companies under the same roof merge, it's usually not a huge deal, right? Just some corporate housekeeping. But when we're talking about Elon Musk's SpaceX and his AI startup, xAI, well, that's a whole different story. This is a move that could seriously reshape two massive industries at once. We're talking about a vision that is, quite literally, out of this world. But before we get into all that, let's just start with the price tag.
Yeah, just let that sink in for a minute. $1.25 trillion. That is an absolutely staggering number, more than the entire economy of many countries. This isn't just a big valuation, it's a massive statement of intent. So what does a number like that actually get you? Well, for starters, it makes the new combined SpaceX the most valuable private company on the entire planet. This is a fusion of two technological titans, the undisputed leader in space exploration, now fused with a very hungry, very ambitious AI challenger. But what is the grand plan behind putting these two powerhouses together?
Okay, so what's the big why behind this trillion-dollar move? The official vision, coming straight from Musk himself, sounds like something directly out of science fiction. The idea is to move our planet's power-hungry data infrastructure into orbit. So let's talk about these data centers in space. Musk himself lays out the reasoning pretty clearly right here. The argument is that advanced AI is just so incredibly power-hungry that our power grids on Earth, they just can't keep up, not without causing some serious harm to communities and the environment. So, what's the solution? Take it all to space. It's a really bold vision, but the reality on the ground paints a much more complicated picture.
And here's where we hit a major point of tension. On one hand, you have the stated goal: avoid the environmental and community damage from these huge data centers on Earth. But on the other hand, xAI has been accused of doing that exact thing at its data center in Memphis. So you've got this clash between the grand vision and the current reality. But beyond the public rationale, there's a really powerful financial logic at play here too.
And that brings us to the financial engine that's really driving this merger. To understand what's going on, you have to follow the money into what some people are calling the revenue loop.
So the first piece of this puzzle is just how much money xAI is burning through. We're talking about an estimated $1 billion a month. To keep that kind of spending up, you need more than just a few investors. You need a guaranteed, massive fire hose of cash.
Now, let's look at the other side of the equation, SpaceX. It turns out they've already perfected a pretty similar model. A huge 80% of SpaceX's revenue comes from launching its own Starlink satellites. It's already its own biggest customer. And that internal economy is really the key to understanding how xAI fits into this whole picture.
So here's how the loop works. Step 1. xAI needs a truly insane amount of computing power. Step 2. To get that power in space, you need a constant, non-stop stream of satellites. Step 3. SpaceX, of course, provides the rockets to launch all those satellites. And here's the magic. Step 4. xAI's massive expenses, they just get funneled right back to SpaceX as guaranteed revenue. It's a perfect closed financial circuit.
And get this, there's a key piece of regulation that makes this revenue loop even stronger. The FCC has a rule that requires most satellites to be deorbited, basically brought down out of the sky every 5 years.
This creates a mandatory, recurring demand for replacement launches. It essentially locks in a predictable revenue stream for SpaceX for years and years to come.
But of course, a vision this grand is never simple. Fusing these two giants creates some pretty significant friction points and controversies. So it's time for a quick reality check on where things stand.
The core issue right now lies in their conflicting short-term goals. See, SpaceX is all in on proving that its Starship rocket can actually handle missions to the Moon and Mars, especially with rivals like Blue Origin breathing down its neck. At the same time, xAI is in a desperate, high-stakes race to catch up to AI giants like Google and OpenAI. These are two incredibly demanding goals, pulling the new company in very different directions.
And that intense pressure to compete has reportedly had some very serious consequences. According to reporting from the Washington Post, the race to catch up led Musk to loosen safety restrictions on the company's chatbot Grok. This allegedly contributed to the tool being used to create harmful, non-consensual AI-generated images of adults and children. Now, for an AI company where trust and safety are everything, that kind of controversy is a massive, massive problem.
So, finally, to really get the full meaning of this merger, we need to zoom out. This isn't just about two companies. It's about how this new entity plugs into the much, much broader Musk tech empire.
When you look at the whole ecosystem, you've got SpaceX for space, xAI for intelligence, Tesla for energy and robotics, Neuralink for brain-computer interfaces, and the Boring Company for infrastructure. Each one operates in a different world, but they're all designed to work together, weaving this incredibly complex and powerful technological web.
And all of this brings us to the fundamental question at the very heart of this empire. Is this a self-sustaining cycle of innovation that's actually pushing humanity forward? Or is it becoming a tech empire with just too much consolidated power under one roof? That truly is the trillion-dollar question. Thanks for joining us for this explainer.